Hello everyone. In this video, we are going to talk about logistic regression. So let's get started. Here is the agenda for this video. First, I will give a very brief introduction to binary classification, and then I will talk about what is logistic regression. Specifically, I will talk about the formulation, the parameters to be solved, and then also the loss function derivations for the logistic regression. And lastly, we will see how to use scikit-learn to train a logistic regression model. So what is a binary classification model? A binary classification model can take as many input features as you like, but its output can only belong to one of the two classes. One example of binary classification model could be a breast cancer detection. So given the tumor radius, texture, parameters, area, smoothness and compactness, etc., those are the input features. The output can only belong to one of the two classes. Class number 1 is the patient has breast cancer. Class number 2 is when the patient does not have a breast cancer. Another example could be a diabetes detection. So given the patient's age, BMI body mass index, blood pressure, cholesterol, blood sugar level, etc., the output can be either one of the two classes. Class 1, the patient has diabetes. Class 2, the patient has no diabetes. Here are more examples. Let's say a banker wanted to know whether to approve a loan or not. This problem can be thought of a classification model as well. So given the applicant's salary, credit score, or employment status, marital status, the model will output either one of the two classes. Class 1, the loan should be approved. Class 2, the loan should not be approved. Finally is the last example, which is the example we will be used throughout this video. We are going to build a model to classify whether an employee is a manager or just a regular employee. So we are going to have two features. The first one is employee's salary, and then the second one is the average meeting per day. Given those two features, we will output either one of the two classes. Class number 1 is that the employee is a manager. Class number 2 is that the employee is just a regular employee. The logistic regression that we are going to talk about today is basically a type of binary classification model. So before we talk about logistic regression, we need to first understand what is the sigmoid functions. So sigmoid function has these expressions. It's basically 1 over 1 plus the exponential of minus z, where z can be as large as infinitive or as small as negative infinitive, but the output of the sigmoid functions will always be between 0 and 1. And on the right, this is the plot between z and the sigmoid functions. So when z is 0, the sigmoid function will output 0.5. When z goes to infinitive, the sigmoid function output will be close to 1. When z goes to negative infinitive, the sigmoid function output will be close to 0. Logistic regression basically plugs a linear combination of the input features into the sigmoid functions and then output a value between 0 and 1. So a linear combination is basically multiplying each input by a weight and then sum them up. So this is an example expression of the linear combination of the input features, where x1 represents the first input features, x2 represents the second input feature, all the way to xm. And then W1 is the weight for the first input feature, W2 is the weight for the second input feature, all the way to Wm. And then lastly, we will plus a beta, which represents the intercept. Summing all the terms up, this is a linear combination of the input features. Once we calculate this, we will plug this calculation z back into the sigmoid functions. And then these sigmoid functions will take any numerical values and then output a value between 0 and 1. And because the output of the sigmoid function is always between 0 and 1, we can think of it as a probability. So we can think of it as the output of the sigmoid functions equals to the probability of the sample being classified into class number 1. And then because the output can only be either of the two classes, the probability of class 2 is simply 1 minus the sigmoid function output. Notice that the output of the sigmoid function really depends on all the weights and then the intercept beta. So I'm using a subscript w and beta to represent that this sigmoid function depends on w and beta, and then this w, which I written in bold, represents a vector of all the weights. To help you better understand logistic regression, let's use manager or regular employee classifier as our example. So over here I have manually created a data set where a company has 5 employees. The first 2 employees are manager, and then the last 3 employees are just regular employees. For each person, I also provide the salary and then also the average meetings per day. If we plot those 5 persons on a figure where the horizontal axis represents the salary and then the vertical axis represents the number of meetings per day, then we can see there are 5 points on this graph. They are color coded. The red color point represents the manager, and then the green color point represents the employees. So remember that in logistic regression, we can think of the sigmoid function output as the probability. So those two are the general expressions for the probability. But how does those two translate into this manager or regular employee classifier? The probability of being a manager is simply using the first feature's salary multiplied by the first weight plus the second feature meetings per day multiplying by the second weight plus the beta. So this expression will give us the probability of a person being a manager. On the other hand, if we use 1 minus this expression, then it will give us the probability of that person being just a regular employee. Of course, the expression of the sigmoid function depends on this w and beta. We will talk about how to calculate those two later, but right now let's just assume that we already get the optimum weight and optimum intercept. So in this problem, the optimum value for the first weight is about minus 3.19 times e to the minus 5th power, and then the optimum value for the second weight is 1.03. The optimum intercept for this particular classifier is minus 0.24. So let's say if we focus on this first employee, which corresponds to this red point here, and we want to calculate the probability of this person being a manager or not, we can simply plug, first of all, the first feature is $130,000 over here, multiplying by the first weight, plus the second feature, which is 5 meetings per day, multiplying by the second weight, and then lastly adding the intercept, feeding all these expressions into the sigmoid functions, we will get the probability of this person being a manager is about 68.4%. Let's look at another example. In this example, we are looking at employee number 3, which corresponds to this green point over here. So the probability of this employee being a manager is equal to, first calculate the linear combination, which has the first feature, which is the salary equals to $100,000, multiplying by the first weight, plus the second feature, which is 2 over here, multiplying by the second weight, and then lastly plus the intercept. Feeding all these into the sigmoid functions, we will get that the probability of this employee being a manager is about 20.32%. Because this is less than 50%, therefore this employee will be classified as just a regular employee. Okay, let's look at a third example. So once we got the optimum weight and optimum intercept, the logistic regression model can work also on a new data. So for example, let's say this company hire a 6th person, and this 6th person is represented by these black points over here, which has a salary of $140,000. And he has about 5 meetings per day. So plugging those numbers into our formula, and calculating the probability, we can see that this new hire has a probability of being a manager equals to 61.14%. Because this probability is greater than 50%, so the model will think this new employee is a manager. You can actually do it for every single point on this figure, and if you do that, you can draw a boundary line on this figure where if an employee's salary and meetings per day is above the boundary line, then the model will think that employee is a manager. On the opposite, if an employee's salary and meetings per day is below the boundary line, then the model will think that employee is just a regular employee. Now let's talk about how to calculate the weights and intercept, because we haven't talked about that yet. So basically, to calculate the weights and intercept, we need to minimize what's called a loss functions. So let's see how to derive this loss function intuitively. And let's go back to our data set, which has 5 employees. Each employee has a salary and then also meetings per day. So the probability of having person number 1 being a manager is simply equals to the output of sigmoid functions. So over here, I'm also introducing a new notation, which is this square bracket after the attributes. The number inside the square brackets represents the employee number. So for example, this 1 represents that it belongs to the first employee. Also, this 1 belongs to the first employee. X1 means that it is the first attribute. X2 means that it is the second attribute, etc. As another example, if the square bracket has number 2 inside it, then it means that it represents the second employee. Okay. So this new notation should be very straightforward to understand. Let's go back to the statement. The probability of having person number 1 being a manager is simply this expression, which is the sigmoid function of the first attribute of the first employee and then the second attribute of the first employee. Similarly, the probability of having person number 2 being a manager is this expression. Okay, the probability of having person number 3 being an employee is 1 minus the probability of being a manager. And then the probability of having person number 4 being an employee is 1 minus that. Similarly, the probability of having person number 5 being an employee is again 1 minus the sigmoid function. Now let's assume that all 5 employees are independent, then their joint probability is simply the product of individual probability. After calculating the joint probability, then intuitively we will want the optimum weights and optimum beta to be the weights and beta that maximize our joint probability. But we also know that the log function is a monotonically increasing function. Therefore, the optimum weights and optimum beta that maximize the joint probability is equivalent to the maximum weight and maximum beta that maximize the log of the joint probability. The benefit of having a log function in front of our joint probability is that we know the log of a product is equals to the summation of individual log, and we use this trick to convert the second equality to the third equality. Over here, we are converting the log of product into the individual log, and by having this, we can further condense the expression by using a summation notation. Over here, I'm introducing a new notation yi. So basically, yi equals to 1 if that person I is a manager, and yi equals to 0 if that person I is not a manager. We can also think of yi as the actual probability of data I, which can only be either 1 or 0. So it means that if person I is a manager, then the actual probability of that person being a manager is basically 100%. If that person yi is not a manager, then the probability of that person being a manager is basically 0%. So that's why I'm saying that we can think of yi as the actual probability of the data. How does this fourth equality equals to the third equality? Basically, when the person is a manager, then this yi will be 1, and this 1 minus yi will be 0. Therefore, this entire second term will be 0. So we are left with only this term. On the other hand, if that person is not a manager, then yi is 0. Therefore, the first term will be 0, and then this expression 1 minus 0 will still be 1. So we are left with this last expression over here. And if you expand this out, you can see that this fourth equality is really equivalent to the third equality. Let's go to the next slide, where I'm already copying the last expression into the first line over here. So in data science field, we like to deal with minimization problem instead of maximization problem. So we can convert a maximization problem into a minimization problem by simply multiplying a minus 1. Also, we like to average this expression here, so we will divide the expression by 5, which is the number of employees. Multiplying or dividing by a constant will not affect the value of the optimum W and optimum beta, so this is a valid operation. Lastly, to extend this expression into a more general form, we are going to replace this 5 by n, representing the number of samples. And we are going to extend these two features into m features, so that we know in logistic regression we can take as many features as we want. And then this entire expression will be our loss function for the logistic regression. The objective for the logistic regression is to find this optimum W and optimum beta, such that this loss function is minimized. We will see how to calculate the optimum W and optimum beta in the next video analytically, but today let's just see how we can calculate this W and beta by the help of scikit-learn Python package. Okay, this is the Jupyter notebook that I have created for this video. So first, I'm going to import the three libraries, matplotlib, pandas, and numpy. This cell is basically generating the sigmoid plot that you saw earlier. I'm going to create z ranges from -7 to 7 with 0.1 interval, and then basically calculate the sigmoid functions and plot them. Okay, this cell is where I'm manually creating our manager versus employee data set. There will be 5 employees. Each one has 3 columns. The first one is the salary. The second one is the average meetings per day. And then the third one is whether that employee is a manager or not. And then I'm going to create a pandas data frame with this data and the salary, meetings per day, manager or not as the column names. After we've creating this pandas data frame, we can print it out to see whether the result makes sense or not. From the df data, let's extract the salary and meetings per day and save that as our input dfx, and then the output y will be the column manager or not. We can also print out dfx and dfy to see if that's correct. Okay, this cell over here is basically plotting the figures of salary versus meetings per day that you saw earlier in the slide. Now let's talk about how to solve for the logistic regression weights and intercept using the scikit-learn functions. So we will need to import the logistic regression module from the scikit-learn.linear model. After that, you can initialize a classifier which I'm named it CLF as the logistic regression parentheses, and then you can use these .fit methods, pass in the input and output. As simple as that, you have created a logistic regression classifier. We can use this .coefficient underscore to obtain the weights. Also the .intercept underscore to obtain the intercept. Those are the parameters, weights and intercept that I have shown in the slide. You can also use these .predict functions, pass in an input to get a prediction result. So the first 2 employees will be a manager, and then the last 3 employees will simply be a regular employees. You can also use these .predict probabilities, pass in the input to get the probability of the output. So the first column represents the probability of each input being a just regular employee. The second column is the probability of each employee being a manager. Notice that each row the summation of the two values should equals to 1, because that's the definition of the probability distribution. You can also make a prediction for a new data set, and it will output the probability as well. Okay, this cell of code is where I am producing the boundary line over here that you saw earlier in the slide. I'm not going to go too much detail on this. Basically, I'm using this contour F method in the matplotlib module. Lastly, let's recap on what we have talked about in this video. First of all, binary classification models take a number of input features and output either one of the two classes. Logistic regression is a type of binary classification models. Logistic regression calculates the probability of class 1 by feeding a linear combination of input features into the sigmoid function. The optimal weights and intercept are the one that minimizes the loss functions. We also derive the loss function definition. And then lastly, we talk about how to solve logistic regression using scikit-learn. This is pretty much for today's video. I hope you enjoy the video. Thank you for watching. If you really like this video, please like and subscribe. I will see you in my next video.